Operating principle of ultracapacitor means how the double layer capacitor technology is charging or getting charged by the actual power source, which is the battery. So you can find here there are mainly 3-4 layers. So main two layers are the collectors, which are very metallic sheets which are shown at the two end of the ultracapacitor. Below is the symbol of the ultracapacitor, and you are finding that between this collector there are parallelogram polarized electrodes. So this left side is getting charged as positive, right side is getting charged as negative. So these are the charges given in black, so plus and minus. In between there is the double layer. So in this double layer there is a reverse charge accumulation you can find here. Because load is not connected, you can find here that capacitor is open still now. So all the negatives are getting attracted towards this positive, all this positive is getting attracted with this negative, and in between there is a separator. Around the separator there are minor charge carriers. So this is connected kind of this is connected like similarity will find with the PN junction diode, and you can find here at the top that the direction of charge is given from right side to the left side. So this is the charger. So this current is coming from the battery, and it is charging this plate and the other plate. So it is like this. So these are the main charge. So these are the all positives these are the all negatives that we are finding here. So the double layer capacitor technology is the major approach to design the ultracapacitor. Here two carbon rods are immersed in a thin sulfuric acid solution separated from each other and applied with an increasing voltage of 0 to 1.5 volt. So this is shown in the diagram. Almost nothing happens up to 1 volt. Then at slightly over 1.2 volt a small bubble appears on the surface of the both electrodes. So here the bubbles are appearing in the electrodes, and bubbles at voltage greater than 1 volt indicate that electrical decomposition of water below 1.2 volt. The decomposition voltage while the current does not flow, but an electric double layer occurs boundary of electrode and electrolyte. So this charge is called as electric double layer. Okay, so this is electric double layer charge, what we are calling. Electrons are charged across the double layer, and for a capacitor an electrical double layer works as an insulator only below the decomposing voltage. So decomposing voltage is here, it is shown as kind of 1.2 volts. So below that the double layer actually is found. What is the amount of stored energy? So stored energy is given by E capacitor, it is equal to half CV square. So as is a capacitor, this is having a capacitance C, epsilon A by D, and whatever voltage you are using, that is actually the usable voltage, it is given in below. C is the capacitance in Faraday, V is the voltage in volts. So you have to understand this more like a capacitor. So capacitor is given some kind of voltage across the two plates. They will be experiencing some charge stored in it. So this is given by half CV square. We are continuing with the operating principle. So E cap is equal to half CV square indicates that the high rated voltage is required for large density capacitor. A capacitor rated voltage with the aqueous electrolyte has been about 0.9 volt per cell. Whenever it is non-aqueous solution or electrolyte, it is 2.3 to 3.3 volt for each cell. What is the advantage or what is the merit for using a double layer capacitor? In place of plastic or aluminum oxide films in capacitor, since the double layer is very thin, the double layer can be one molecule thin or without any pinhole. That means there is no puncture in the layer. So the capacity per area is 2.5 to 5 microfarad per centimeter square. This is quite big. So this is the merit of using electric double layer in place of plastic or aluminum oxide films. So even if a few microfarad per centimeter square are obtained, the capacitor energy density is not large with the aluminum foil. To increase the capacitance value, activated carbon electrodes are made with very large area, like surface areas of almost 1000 to 3000 meters square per g. G is the gram. Okay, that means the mass is very small. Meter square per gram means mass is very small, that is given in gram, and area is very big. So whatever 1 gram of material is taken, that has been stretched for an area of 1 meter square. Energy density of these capacitors is smaller, very small actually, than the batteries. So I told you that the supercapacitor is, or ultracapacitor, it is not a high specific energy device, but it is a high specific power device. Hence energy density of these capacitors is far smaller than the batteries. Batteries are actually charging this ultracapacitor. Typical specific energy of ultracapacitor is 2 watt hour per kg. So this you have to remember, which is only 1/28th of 40 watt hour per kg, which is the typical energy density of a available lead acid battery. So these are some of the details, specifications you must remember. That is, battery is having average watt hour per kg, that is the energy density, which is around 40, whereas the energy density of ultracapacitor is 20 times less than that, it is 2 watt hour per kg. Performance of the ultracapacitor. So the ultracapacitor performance is represented generally by the terminal voltage. We have shown the symbol, and you are finding there are 2 terminals, and the terminal voltages are measured during charging and discharging also, and there are different current rates. So during battery we have shown you that from the same battery different current rating can be obtained. So if the current rating is more, that means higher current you are trying to fetch from the battery, in that time the battery initial voltage drops. If the current rating is high, in that case you will be finding battery can give you very high initial or starting voltage. So there are main 3 performance parameters of ultracapacitor. Number 1 is the capacitance itself, for a certain electric potential which is given by Vc, voltage of the capacitance. Series resistance Rs. So we are going to model the ultracapacitor shortly. We have seen some model of the battery. There was an internal resistance. In case of this ultracapacitor, there is a series resistance which is given by Rs, and there is a dielectric leakage resistance. Though we have said that there are no pinhole effect in the junction, but there is some leakage. That means some charges actually get recombined from the positive side to the negative side. Now this is one question which can be asked in the exam, that is, what is the equivalent circuit of ultracapacitor. So you are finding here, so this is the ultracapacitor which is having a electric potential Vc, this is the capacitance, and this is the voltage across capacitance, this is Ic, how much current the ultracapacitor is giving out, and you are finding that there is a RL. Okay, so this is that leakage resistance. So RL is in parallel with the capacitance C, but you are finding there is a Rs which is in series with the capacitor C. And whenever I am saying capacitor C, it is actually having C and RL in parallel. So this Rs is in series with the parallel combination of ultracapacitor capacitance and ultracapacitor leakage resistance. So this I is the current of discharge whenever this Vc is full. After that, if you are asking for some more current, in that case you will be finding that Ic will be the actual current delivered by the ultracapacitor. In that case, the load current is I. So between this positive and negative, you can connect the electric load, which can be the motor of the vehicle. And RL actually internal resistance, leakage resistance of the ultracapacitor, that also will be eating up some of the current. So this Ic is equal to IL plus I. This you have to remember. Ic is equal to IL plus I. Very simply, if you apply KCL at this junction, you will be finding that whatever total current is sent by the ultracapacitor, that is getting divided into 2 parts. One is the load current I, another is the dielectric leakage current. This is given by IL. This is the ultracapacitor equivalent circuit. Terminal voltage of an ultracapacitor during discharge can be Vt, that is Vt is found here. Okay, Vt is equal to Vc minus I into Rs, where I into Rs is called as the internal voltage drop. So Vc is the actual voltage we are finding across the ultracapacitor when the load is not connected, which is called as the potential difference between two plates of the ultracapacitor. Two plates can be talked about as the electrodes. Now that VC is actually reducing little bit because there is a internal voltage drop, that is this I into RS. If you have to subtract from VC, then you are getting what is called as a terminal voltage. So this terminal voltage is actually connected to the motor which you want to run by the ultracapacitor. Electric potential of the capacitor can be expressed as, so electric potential is dVc dt is equal to minus I plus IL divided by C. So I plus IL, whenever I am saying I plus IL is nothing but IC. Okay, so IC by C, and negative here C is the capacitance of the ultracapacitor, and this is while you are actually discharging. Whenever I am saying that how the capacitor is discharging, what is the rate of discharge of the capacitor. So this is given by dVc dt, which is minus. So this minus comes because the capacitor is discharging now. This is nothing but IC divided by C, or I plus IL divided by C with a negative sign. Leakage current is given by VC by RL, okay, which is a very small current, which is given by IL, leakage current. And this is the ultracapacitor model you are finding. So this is a VC. This VC is given by minus 1 by CRL. That means this is a drop. After that, whatever thing is coming here, so then minus 1 by C. So minus 1 by C is nothing but the ultracapacitor actual capacitance. So these two are the internal components, 1 by C and 1 by RL. Okay, and they are actually generating the voltage. So whatever voltage you are finding, it is going at the output side. And you can find here, if you want to find this I plus IL, or if you want to find the IC, that will be nothing but an integration of this whole thing. Okay, so dVc dt is equal to like this. So if you want to find IIL, then you have to integrate this thing. So that's why this integration sign is there. And if you are integrating this current IC, then only you can get what is called as a terminal voltage VT. So here you are finding, so this is like the block diagram approach you have seen in control system in second year. So here you are finding the VT. VT is nothing but the terminal voltage, and this IC is having a component of RS. Okay, so whenever I am saying minus 1 by C, this is the voltage produced by the ultracapacitor. This VC also, this will be having a component, this ultracapacitor, which will be reducing its voltage. So it will be reducing the voltage by I into RS. So you can find here that here is a division, okay, and this I into RS, so this is the I part, it is actually in a subtractive mode with this total VC. Okay, so this VC minus I into RS will be equal to VT. This is the ultracapacitor model. This is the ultracapacitor. This actually left side is the circuit model, right side is the block diagram approach of ultracapacitor model, and the equations are dVc dt is equal to IC by C. This is during charging, you can say, and this is during discharging. dVc dt is equal to minus I plus IL by C, that is equal to I by C plus VC divided by C into RL. So C is the ultracapacitor capacitance, RL is the leakage resistance. So this slide is the most important slide as far as the performance, internal construction and performance parameters are concerned. So please prepare this slide properly. Performance of ultracapacitors, you are finding the terminal voltage VC, how it is modeled. So it is modeled by VCO. That means whenever the ultracapacitor is open circuited, that means you have not connected the load yet. So how this VC is reducing? So it is VCO minus I by C. So I is the current that is flowing to the load, C is the capacitance, T divided by CRL, as is a capacitive thing, it will be having a time constant. So the time constant is given by C into RL. So this is the first time constant which is actually having two components. One is the ultracapacitor's capacitance, and another is the ultracapacitor leakage resistance. These two together is deciding how fast or how slow the ultracapacitor will charge or discharge. So this is the first part. This whole voltage will be discharging e raised to minus t divided by CRL. Discharge current I is a function of time, obviously. So this is I is a discharge current. You are finding this corresponds to VT, that is the terminal voltage. And the discharge characteristics is given in the right side. So if I'm asking you performance, in that case you must have to draw this discharge characteristic as well. And here finding that if you are asking for more discharge, you can, if you remember these terms, the specifications, in case of ultracapacitor, the first discharge current is starting from 50 ampere, then 100 ampere, 200, 300, it is going almost up to 600 ampere. And whenever it is 600 ampere, its terminal voltage is 2 volt. Wherever it is 50 ampere, its terminal voltage is almost 2.45 volt. Two things I would like to draw your attention to. First thing, starting voltage in case of battery was around 2.03, okay, for lowest discharge current of 10 ampere. In this case you can find out that suddenly the current has jumped up. So for battery the lowest discharge current was 10 ampere, but for ultracapacitor the lowest discharge current is 50 ampere. For battery it was going almost up to 100 ampere or so, but in case of ultracapacitor it is going almost up to 600 ampere. So you can find out how big ultracapacitor can discharge. But this very big discharge of 600 ampere, that means you are asking for too much current from the ultracapacitor. It cannot stand for more than 18-20 seconds. If you can find here, it is exactly the 600 line is dropping exactly at the center. That means the 600 ampere current maybe will last only for the 10 seconds. Even if you are taking this 50 ampere current, x-axis is discharge time, and you are finding is that it will touch somewhere here, which will be around 125 seconds. So 125 seconds means 2 minutes. So what you have to see here is ultracapacitor can give you very high current of 50 ampere, starting from a voltage of 2.5 it will get discharged, and it will be giving you 50 ampere current. But this 50 ampere current will not be given for throughout the driving period or so. This 50 ampere will be given only up to 2.25 or 2.5 minutes or so. That means hardly 120, 130 seconds or 140 seconds. Okay, not even 140 seconds you can find here. So this is what is the ultracapacitor about. It is giving you the bumper high specific power during heavy requirement. So requirement also has to be heavy, and power discharge also will be very heavy. But all those things can happen only for a very short period of time. And how short it is around 2.5 minutes or so. You can just go through, that is the discharge characteristic of a Maxwell 2600F ultracapacitor. So Maxwell is a company which is preparing this. Is shown here at different discharge rates, the voltage linearly decreases with discharge time. You can find here the voltage is linearly decreasing with discharge time. So as time is progressing, the discharge is coming almost to zero. At a large discharge rate, the voltage decreases much faster than a small rate. So here the discharge rate is 50 ampere. It is taking quite a lot of time. It will be going up to almost 130 seconds. But if you are getting discharge at 600 ampere rate, in that case you will be finding that within 10 seconds the whole ultracapacitor will get discharged. So this is its job, to give very high current at the output whenever the motor is trying to escalate, or when the motor is trying to go up through the hill, okay, or through the mud, or maybe very high acceleration is required when the motor is on the highway. At that time only there will be the requirement of this kind of very highly dischargeable ultracapacitor. So this performance characteristics is very important. So these two slides, previous slide and present slide, so this is the performance of ultracapacitor and another performance of ultracapacitor with the graph. So these two things are very important. Then again there is coming another slide which is charging efficiency and discharging efficiency. So you are finding that this is charging efficiency. If you are charging with 600 ampere rate, in that case within you are finding that by around 2.5 volt you can go if you are charging with a smaller current rate. So exactly the same thing happens in case of discharge also. If you want it to charge very fast or something, but in that case you cannot go beyond 80% or so. Okay, so very high current charging you cannot get the ultracapacitor charged to the 100% extent. So this is another thing you have to understand. Same kind of thing happens in case of battery also. Too much of high charging current, you cannot take it to maximum 100% of charging. So go slow, give time, and let it get charged slowly. So x-axis is terminal voltage, so there is no time here. Time parameter is not shown in the graph. It is only discharge or discharge efficiency. I'm sorry, it is actually talking about discharge efficiency, not charging. But this discharge efficiency, same thing. That is, you can get maximum 100% discharge when you are actually going at a lower rate. Same thing is shown in the previous slide also. That is, if you are going at a lower rate, 50 ampere, you can get a discharge for longer period of time and with higher efficiency. That is shown in the slide here. Okay, and if you are discharging very fast rate, in that case you are going to get that within maximum discharge you can get up to 80%. That means you are not going to utilize the full charge whatever is given in the ultracapacitor. So discharging efficiency, eta D. D stands for discharge. It is Vc minus Rs into It. It is terminal current divided by Vc. So Vc, whatever was the voltage stored in the ultracapacitor, Rs is the internal resistance. As Rs into It is very small, because Rs can be in very small value, maybe 0.3, 0.4 ohm or something. So you can say that Vc minus Rs It. So this whole thing can be called as a Vt, and Vt and Vc, they are very close, but there will be some difference. Okay, so this discharge efficiency you can take to very high value. Charging efficiency is just reverse. It is Vc divided by Vc minus RSIT. So whatever is the output in case of discharging, the same thing will become input in case of discharging, and whatever is the input in case of discharging, that will be the output in case of charging. So it is Vc by Vt in case of charging, and it is Vt by Vc in case of discharging. Vc is the ultracapacitor voltage, Vt is the terminal voltage which is connected to the motor. Equations indicate the energy loss in ultracapacitor is caused by the factor Rs. Rs is nothing but the internal resistance, series resistance. The efficiency decreases at a higher current rate and low cell voltage. So if you are finding that discharge, if you are doing 600 ampere rate, it will go maximum up to some 2.1 volt or something. Okay, but if you are doing the same thing at lower current rate, might go up to, you might get actually bigger voltage across the Vt. That means Vt voltage will be higher if you are going for lesser rate of current. This is actual operation. The ultracapacitor should be kept in its high voltage region for higher than 60% of its rated voltage. That means your current discharge rate you should fix properly, so that always you are going to get some higher voltage across the terminal. Ultracapacitor efficiency. So this is just a slide given. If you remember, the EC is equal to half CV square, that much also will do. Here Vc is the cell voltage here. So intermediate equations, if you cannot remember integration, it's okay. Only you have to remember that potential across capacitance is half C into Vc square. Vc is the cell voltage. As a rated voltage, the energy stored in the ultracapacitor reaches its maximum. Equation above indicates that increasing the rated voltage can significantly increase the stored energy, since the energy increases with the voltage squared. In real operation, it is not possible to completely utilize the stored energy because of the low power in the low state of energy. So you have seen SOE. So SOE is another parameter which is called as a state of energy. This is also given in percentage. SOC you have seen state of charge. So state of charge requires measurement of voltage, current, and other thing. Another way of determining how the battery is functioning, or what is the characteristic of the battery at any time, it can be found by state of energy. So state of energy and state of charge, they are two different parameters. Ultracapacitor is usually given a bottom voltage CB. Okay, so here you are finding CB, and below which the ultracapacitor stops delivering energy. Consequently, the available energy for use is less than the fully charged energy. So that is given by CR. which can be expressed as, okay, actually this EU, okay, how much will be the range of the ultracapacitor utilization voltage. So VCR is the rated voltage of the ultracapacitor, and CB is the bottom voltage. So you should not go beyond the bottom voltage. So minimum you can touch is the bottom voltage. So what is the overall energy change or energy dissipation by the ultracapacitor? It is given by utilizable energy is equal to half C into VCR square minus VCB square. So CR is nothing but the rated voltage and CB is nothing but the bottom voltage. So this half C VC square, it is modified into half C VCR square minus VCB square. Usable energy in ultracapacitor is given in SOE. So SOE is 0.5 C VC square divided by 0.5 C VCR square. Okay. So C is generally whatever we get from the rating of the ultracapacitor, that is VC, and what is CR actually is the rated voltage of the ultracapacitor. So VC is the actual voltage and CR is the rated voltage. Rated voltage means whenever you are purchasing the ultracapacitor, it's a new thing. At that time, whatever is the voltage we find, that is actually called as a CR. This capacitor is rated for this much voltage, but while utilization, you will be finding that it is not going up to that much part. Okay, so it will not, VC will not be V equal to VCR after usage or after few cycles of charging and discharging. This is the SOE versus cell voltage graph. You are finding that x-axis is the cell voltage, y-axis is the state of energy. So you are finding 60%, that is 1.5 volt is 60% of 2.5 volt. So here you are x-axis. So whenever I am saying that cell voltage is 2.5 maximum, so 60%, what is 60%? 60% is 1.5, that means here from 1.5 up to 2.5. So this region, okay, so this region, that means 1.5 volt to 2.5 volt of input of the rated voltage is the bottom voltage, and 64% of the total energy is available for use. So that means whatever energy you are given, that is available 60% from 1.5 volt to 2.5 volt. So as you are getting discharge from the ultracapacitor, you will be finding that your voltage is dropping across the ultracapacitor terminal. So when you come to 1.5%, you actually used the voltage drop is from 2.5 to 1.5 is 40% voltage drop, but you have used the energy of 64% because of this slope of this curve. Okay, so within 40% from the peak, actually you are using the energy of 64%. So this graph is little difficult to interpret, that's what I have kept it, but if you look it properly, you will understand that whenever you are in between 1.5 to 2.5 volt range for the ultracapacitor, 64% of the usable energy is available in this range. That is area under the curve. That means you have to calculate this area, okay, under this 1.5 to 2.5, and you have to calculate the overall area. Okay, and overall area is, if you consider 100%, so 1.5 to 2.5, whatever area is there, that is nothing but 64% of the energy of the overall, that is 0 to 2.5. This is what is meant by this graph. This is SOE versus cell voltage, that is state of energy versus cell voltage graph. This is a direct parallel connection of batteries and ultracapacitor. You can find here that a lot of batteries are there in the left side. Batteries we have already seen. This is a high energy, high specific energy source, which is actually kept for longer range of the driving, and then ultracapacitor is coming in parallel, so that this ultracapacitor can get charged from the batteries. So there will be means, that means some switch will be kept in between. Generally the batteries will be delivering the terminal voltage, and whenever there is a peak demand, PEAK, whenever there is a peak demand at that time, ultracapacitor also will chip in and it will be delivering the required voltage. Various ultracapacitor technologies, so you can just go through this. Maxwell is one company, I told you. Power Bootstrap is another company, and there are many specific energy and specific power ratings are given. So advanced performance value should be 15 watt hour per kg and 1600 watt per kg or 1.6 kilowatt per kg. So this is specific power rating, this is specific energy rating. And this is the various ultracapacitor technologies: BCA P0010, BM B mod 0115, B mod 0117. All these are different companies. So these last two slides are just for your viewing. It will not be asked in the exam. So this finishes the various ultracapacitor technologies, or different things about ultracapacitor. As far as question is concerned, these three slides are very important. That is performance of ultracapacitor. These are the four slides which are very important. Definitely I'm not going to ask you construction or operating principle of ultracapacitor, but yes, you should know the operating principle of ultracapacitor. So I'll be posting the questions related to this thing in the group. Wherever it is uploaded, there only the questions related to ultracapacitor will be uploaded. So we have completed the third lecture in module 3, and we have completed battery and ultracapacitor completely. Thank you.